Hello everyone, welcome to this video. In this video we are going to discuss about what is PCA and LDA. So the principal component analysis and linear discriminant analysis. So these two algorithms we know very well, so that is helpful as in the feature extraction part. So it was used for the dimensionality reduction and feature extraction. So how these PCA and LDA is helpful in the statistical technique in our biometrics, especially in the multi-model. So that is the thing we are going to discuss here. So principal component analysis, it's a cornerstone, it's a statistical technique in the biometrics. So that is majorly we are using for the dimensionality reduction as well as a feature extraction. So by transforming the high dimensional biometric data like images into the smaller set of uncorrelated variables. So that is called as a principal components. So the PCA making the identification system in a more faster as well as in a efficient way to getting the essential identifying the features. So what are all the core applications in biometrics working under the PCA in the sense? It's a Famously, it is associated with the eigen methods, that is, the eigen face method for the face recognition. So, but it's utilizing the extended level. It's a several other biometrics model too. We can do it. So, face recognition and fingerprint recognition, ear biometrics, or even in a multimodal fusions. So face recognition, we can able to finding the new faces or identifying the faces. So by based on the face shapes and comparing their coordinators to the coordinates to the known individual using the distance metrics like Euclidean distances. So similarly, the fingerprint recognition, so that extracting the statistical features from the ROI region of interest. So based on that is also enhance the fingerprint images by filtering out the background noises and trying to focusing on the principal ridges patterns. I look. Similarly, for the ear patterns, it is extracting the geometrical features of the ear to creating the compact template for the verification. So often this will be used for the mobile paint authentications. So similarly, we can able to apply for the combination of the two different sources, that is called as a multimodal fusions. So how the PCA works? So the PCA works in the biometric context. It's a typically the workflow. It is involving the several mathematical steps, so that is trying to translate the physical traits into the digital signature. So the first step is the image representation, that is going to be convert the biometric sample into the long 1D vector, so one dimensional vector, like that it is going to be constructed. Then mean subtraction, so that is going to be calculate the average biometric from the training set and it subtract from the every sample to the centers. The next one is the covariance matrix. It's going to be calculate how the different pixels or features varying together across the entire the data sets. So then eigen decomposition, it trying to solve the eigenvectors and eigenvalues of the covariance matrix. Then finally the dimensionality reduction. So the dimensionality reduction, they are just keep only the L eigenvector, that is which one is having the largest eigenvalues to form the lower dimensional feature spaces. So that is effectively working with preserving the most unique characteristics features. So what are all the benefits and then limitations of the PCA? The complexity wise, it is reducing the data storage and computational cost by working with the smaller dimension, but it is struggling in the non-linear data. So when the data in patterns are non-linear, in the sense in that cases it will be getting the more struggle. And noise, automatically it is ignoring the small variations, so that is a background noise are going to be removed and focusing only on the maximum variances. But the same case and highly sensitive to the changes, illuminations or pose differences or facial expressions. In that cases, that too it is considering as a noise and it is eliminating the important features. So when the training cases, it's a unsupervised learning, it can find the patterns without need any pre-labeled data. but it requires some precise image registration, so some alignments to be there to work more, get accuracy. These are all the things based on their performance. So what is LDA in the sense? It's a linear discriminant analysis. So LDA it's a supervised learning technique, so that it's sure having some labels. So this is also going to be work for our dimensionality reduction and classification. So unlike the PCA, so it is focusing on the maximum data spread, but the LDA it is identifying the features best separate from the people in the data set. That is the main difference between the LDA and PCA. So the core applications in the biometrics for the LDA, it's highly effective in the system of where the goal is distinguish between the specific individual. So like the face recognition, fingerprint and iris recognition, and even the attendance and the access control systems. So all these things are considering as a core applications in the biometrics of we can apply in the LDA algorithms. So how the LDA working process means, so the computational process aims to find a new feature space where the distance between the different classes or peoples. So it is a maximized, so when the spread within the same class should be minimized. So first it's computing the mean vectors, it is calculating the average feature vector for the each and every persons or classes. So it's an overall average of the entire data space. So the second thing it's going to be calculating the scatter matrix. So within class scatter matrix or between the class scatter matrix. So both the thing it's going to be considered. So here the class is nothing but the people. So within the people, what are the features the scatters, and then between the two different peoples, what are the features are going to be, how it is a measure, the distance, how it will be there. So then finally solving the linear discriminant. So it's finding the projection vector, it's a W, so that is maximizing the ratios between the class scatter to the within the class scatter. So then next step, it's a project the data. So it's transforming the original high dimensional biometric data into the newer one. So it's a low dimensional access to create compact and highly it's a discriminant representation. So what are all the benefits of LDA in the sense? LDA is going to be working with a superior separatability. So it's a dimensionality reduction it will be working. So it is shrinking the large image data into these smaller ones by reducing the computational cost, as well as it is working with the most efficiency, and how it is efficiency means less computational cost, it is intensively it is not focusing on the non-linear methods, so it making it suitable for the real-time identification. So what are all the limitations of this LDA? The first thing is a triple S problem, that is a small sample size. If your sample size is very smaller, so obviously LDA will get 5. Okay, so the sample size should be in a more. So the normality assumption, so assuming the data follows the normal distribution, that is a Gaussian distribution, so the performance drop if it is not in the true cases. So then linear constraints, so linear constraint it cannot capture the complex one, so non-linear relationships in the data, so that is the extreme post changes, in that cases it will not identifying in proper way. So the comparison between the PCA and LDA, the key differences in the biometrics, how it is working. The first thing is based on their objective. So the PCA objective is for the features, and that is a variance calculation, but the LDA is looking for the differences, that is a separatability, how more it is a classified. So that is the focus of the LDA. So the objective of this thing, features and then differences. So learning type, how it is learning. So PCA is a unsupervised, it doesn't know which image belongs to the which person. So there is no, it's a simply finding the direction of the maximum spread. But the LDA is a supervised one. So supervised in the sense it needs some labels. It is identify the labels to finding the axis, and based on that it is maximize the distance between the different individuals and minimizing the spread of the same person. So that is a main differences in the learning type. So PCA is unsupervised and LDA is a supervised one. Then finally the dimensionality reduction. So the PCA can extracting the many components as their features, but the LDA it's limiting to the components, that is the features are going to be maximum as a C minus 1 component. So C here is nothing but the number of the classes or otherwise the number of the persons who we are going to be compare in our database. So the performance wise in many biometric studies the LDA is giving their higher recognition rates compared with the PCA. Because of that it is providing the nearly the 97 to 100, so nearest to the 100 percentage it is going to be work on it. So the LDA is preferable for the many biometric studies. So which algorithm where we can use it, so what kind of the scenario, so which algorithm or which methodology is perfectly suit for that. So for example, if you have a small training data sets, so you will be working with the PCA. So the LDA can overfit if you have only the 2 to 3 images. If you have a less training data sets or less kind of the data, so obviously in that cases LDA is not suitable. That is the limitation of the LDA. In that case only the PCA is the preferred method. So when the data set or labels are so large, so in that cases the LDA is a more perfect. So LDA's ability to focus on the discriminant features, so it makes it a superior for higher accuracy identification. Similarly, so the variable lightning or different kind of the poses, if it is there, in that cases also we can go with that LDA. So it's a LDA is a generally it's a more robust to the environmental norms. It doesn't changes the person's identity, so that we are just picking the LDA in the cases of the various lightning or poses differences. And the step-by-step procedure of the PCA and LDA. So the first thing is the PCA. This is the mathematical steps of the PCA, so eigenphase logic. So the first step we are just going to be organizing the data. So here the X is the creation of the matrix of the each and row. It's a sample of biometrics. For example, the eye width and nose length, like that we are just taking. So that is a coordination we are just mentioning as a matrix. So then we are calculating the mean subtracting. So using the mu value. So mu is nothing but it's a each feature, so that is a subtract from the every data point. So from the X we are just subtracting. So the next we are just calculating the covariance matrix using this formula of C. So then finding the eigenvalues and eigenvectors. So both it going to be calculated. So eigenvalue is denoted by the lambda and eigenvalue denoted by the small b. So this is the actual direction of the principal components. So that's the eigenvectors. So eigenvalues are telling us to the energy or importance of the each and every directions. So the next step it's a projecting the data. So the now it's going to be multiplied with our original data with the top eigenvectors to get reducing the phase shape coordinates. So this is the step. So now we will just look on with some sample example. So how the PCA is going to be work on it. So here the 2% samples we are just taking the eye width and then nose length. So that we are going to be considering as a matrix. Eye width samples, so divided by 4, so we are just calculating the mean values. So that is mu equal to 3.5 comma 6. So 2 2 and 5 5, that is the eye length, and then nose length 3 4 and 5 8, like that we are just calculating. So both the persons eye width and then nose length we are just taken. So then we are just center the data. So we are just finding the X values, the minus from this. Okay, so 3.5 minus 2, sorry, x minus your mu value. So the formula is z equal to x minus mu. So x value is 2, 2 minus 3.5. So minus 1.5. So like that we are just calculating for the all the input values. So then the covariance matrix are going to be calculated. So using this formula, so z transport multiplied with z, so we will just getting this value. So then finally we are calculating the eigenvalues and eigenvectors using the formulas. So this is a principal component showing the direction of the maximum variance. Okay. So now the same example we will just apply with the LDA. So this is the steps for the LDA. So the first step we need to calculating the class of the mean. So for the each person's mean value, so mu1, mu2 like that we are just calculating. So the overall mean is considering as a mu total. And next step we are just calculate within the class scatter matrix. So this is measure how the person's features are going to be vary. So using this formula we can be able to do it. And the next step is calculate between the class scatter matrix. So between the class scatter matrix, so that is a SB denoted by using this formula we will just calculating the between the class scatter matrix. And next step finally we are just calculating the eigenvalue problems. Okay. So the between this class scatter matrix and within the class scatter matrix, so we are going to be multiplied, and with along with that our eigen vector value. So that is a finally we will just getting the lambda b. So your eigenvalue and eigenvectors. So then we are just selecting the linear discriminant. We are just short the eigenvectors by their eigenvalue. So the highest lambda is providing the best separation between the individuals. So this is the example of we can apply the same steps here. So the first class mean mu A and mu B, so two different persons information we are just taking. So then second step we are just calculating within the class scatter matrix, that is the SW we are just calculating using this formula. So since I width is a constant for the each and every person, so we are on that we are just minus. And second step between the class scatter matrix we are just finding. And finally the solving for the SW inverse, that is SB. So in the real system we are just adding some tiny values for the SW to make it to the invertible. So inverse of the matrix we are just taking. So finally the eigen values and eigen vector calculation. So you will get the lambda value is a 2.5. So that is giving the higher value indicates excellently it's a separatable. So then eigenvector 0, 1. So this axis is perfectly, it separates the between the two different persons. So what is the core differences between the PCA and LDA based on these results? So the first thing, the PCAs are finding the clouds of the point in the longest, so who are all just going to be the closest together. But in the LDA it is finding the best friends, that is nothing but which one is how it is deviating. So it is mainly it's working for the classify, so which one is it's giving the largest value, so how it's easily separate by one with another one. So like that it is identifying. So the eigenvalue, so here the variance, so that is how it's spreaded together. So that is the PCA result. And LDA it is a discrimination. So there is a separation of the eigenvalue, it's indicating the it's a separation of one feature with the another feature. So in the use cases we can able to apply here for the PCAs nearly the 50 features among the 50 features to who are all the closest together. But in the LDA we are just going to be identify whether the given feature is belongs to this person or another person. So that kind of the identification we are just working with the LDA. So this is the main differences between the working principles of PCA and LDA. So we will just look into the another session. Thank you.